All right, welcome back. So in the previous video, we discussed what a goodness of fit test is and why we really care about doing it. So here, let's just go ahead and see an overview of the steps to complete the goodness of fit test, as well as do an example. So again, just to recap, we're going to start with the assumption that the proportion of distribution in our experiment is given or follows something that is known. So it's either going to be given or is known. Then we're going to go ahead and say, okay, I'm going to take a sample, and then I'm going to compute the number of data points that I expect to observe for that sample size. So given a sample size, if you know what fraction should be in each category, you can go ahead and compute the expected observations. And the expected observations are found with a very simple formula from binomial experiments, where we go ahead and take the proportion of individuals in category I and multiply that by my sample size. And that gives me the number of expected values that I expect in category I. So now we have something to compare against. And this quantity is going to be called EI, in other words, the expected count in category I. Now that I have an idea of what should happen for every single category, I can now compare that to the distribution that I get from my sample. And then what I'm going to do is I'm simply going to say, well, is there agreement? Can I quantify the level of agreement or disagreement between the observed? So when you collect the sample, you're going to get what are called the observed counts in category I. And we're basically going to say, is the observed value that we see in I very close or about the same as the expected value that we computed? If the answer is yes, right? So if OI is relatively close to EI for every category, that's what we expected to see, because the observation was that, yes, my data does follow this distribution. Then there is evidence to support the claim. We support that the data follows the claim distribution. However, if we have our observed value very different, from the expected value in a few categories or many categories, then we're going to go ahead and say that our assumption is probably not correct. Then we're going to reject the claim distribution. All right, and it's as simple as that. This gives us what's called a goodness of fit test. This procedure here is literally the goodness of fit test. And it's very easy to see where that name comes from. We're essentially quantifying the level of agreement or disagreement between the observed and the expected. So this gives me the steps for the goodness of fit. So notice the hypothesis, we're going to say the random variable or our distribution fit or follows whatever it is that is claimed. And the alternative is that that is not true. That is not the case. So let's go ahead and now present the requirements. What were the assumptions? And we're still going to have the same assumptions, SRS, independence. But now we have a slightly different requirement, because it's not about the shape, but rather the expected count. So this is going to be one of the new differences that we need to watch out for. And what you're going to do is you're going to base it off of the expected counts in I. So there's two checks that we need to do. The first one is all expected counts are greater than 5. And so a shorthand way of writing that is that EI is greater than or equal to 5 for all I. So for each category, you want to make sure that your expected counts are not very small. Part of the reason is that you will reject the null hypothesis just because the number is very small. Okay, so this again has to do with requirements that are known to ensure that this is a proper test. Same thing with the last one, is that no more than 20% of the expected counts are less than or equal to 1. Oh man, you know what? These are actually backwards. Not sure where that 5 came from. All right, so let's emphasize that. All expected counts are greater than 1. There we go. And no more than 20% of the expected counts are less than 5. Maybe let's just use less than. Okay, that makes sense. Cool. So originally I wrote those in backwards, so please make sure that you got the correct counts. All of the expected counts are greater than 1. So again, we don't want very small values in our expected counts. And the last one says that you also don't want very small or just smallish numbers in a large fraction of your expected counts. So that's what the second one is. All of this is experimental here. So this is known to give good results. So these conditions in red are known to lead to proper, correct outcomes. And so that basically means if one of these is not satisfied, for example, you have 40% of the expected counts very small, then you're going to reject just because the expected counts is very small. Okay, it's like a mathematical reason. All right, so these are the new requirements. Everything else here is familiar to us. You've seen this before because the distribution, the level of disagreement is going to be given by the statistic right here. So notice that this quantifies the level of disagreement. Chi-squared. So you're going to take the observed, so that's the sample value, minus your expected, so subtract them, and then you're going to square them to make it positive. You're going to divide by the expected, and that way it gives you a fraction, like from the expected. So this quantifies some fraction of disagreement for category I. And then you just do that for every single category. So you'll add that over all I, and you essentially get a value for the level of disagreement. That distribution, that statistic is known to follow a chi-square distribution with k minus 1. Remember, k is the number of categories. And a chi-square distribution looks like this. Now, because we're trying to determine whether this is, there's a lot of disagreement, in order for us to support that the fit is not what was claimed to be, you're always going to be performing a right tail test. Because again, we're trying to say if the difference is large enough. So small difference, that means that there's going to be a small test statistic. So you'll land over here. And if there's a small difference, that means that OI and EI are very close to each other. So this will always be a right tail test. Just like that. And the rest of it is exactly the same as a regular hypothesis test. So I want us to go ahead and just practice this by hand. This is going to be the only time we're going to do this by hand. And I'll show you how to do this using StatCrunch right after. So here's our first example. It says, assume we consider 4 different categories. So again, here's category 1, category 2, category 3, category 4. The categories could be anything, could be, age range, ethnicity, could be a kind of treatment or a group that you're actually with. And we're going to go ahead and say that suppose that we know the distribution. So here's the claim. From that claim, we get the PI, where category 1 has 20% of the individuals. Category 2 is going to get 10% of individuals with some trait or characteristic. And we just keep going. Okay, in other words, we know the proportion, like how often category 1 would appear. So you can think of this as like a scale. You can ask someone, do you agree or disagree? So maybe here they are satisfied, level 1, level 2, level 3, level 4. So if it's a satisfaction survey and you're saying this is how people are going to respond, we can now go ahead and determine whether that's true or not. All right, so remember, you always start with that. You're given a sample size and you're also given some kind of distribution. So we've got that now. Let's go ahead and compute the expected counts. So always go ahead and do this. So this is what we expect. Remember that the expected counts, this would be E1, is equal to the sample size times the proportion of success in that category. So in this case, this will be 400 times 0.2. Throw that into a calculator, we get 80. Let's continue doing this. So this will, again, this will be E2. That'll be 400 times 0.1. That gives you a value of 40. E3 is going to be 400 times 0.45. Throw that into a calculator. We get 180. And then finally, for the last one, we're going to get 100. So hence, we've got our expected counts. What I want to point out is that if this is true, if my claim is correct, that this is the actual distribution for each category, then the expected count should agree with our sample. When you actually take the sample results, these are called the observed count. So this is O1. I observed 100 individuals. Under the null hypothesis that this is the actual distribution, I should have observed 80. Now, that's kind of close, maybe, potentially. Look at category 2. I actually took my sample. I observed 50 individuals in category 2. According to the null, I should have observed close to 40. So again, that's pretty close. Okay, and we just kind of keep going. So observed 3 was 150, observed 4 is 100. And here we actually do get agreement. All right, before you continue, I'm just going to say this out loud. I didn't write the hypothesis. This is just more or less emphasizing the procedure. And we need to go ahead and check the requirements. SRS independents are going to be safe to assume. We will only check the expected counts. So let's go ahead and go through the motions here. Condition number 1, is each expected count greater than 1? You do this by eyeballing it. Here are the counts that we expect. We expect to observe 80, 40, 180. That definitely holds. Each of those values is greater than 1. And then finally, no more than 20% of the expected counts are less than 5. How many of the counts here are less than 5? None. Each. So let's go ahead and get a proportion for the number of expected counts less than 5. We have 0 out of how many expected counts? 4. That translates to 0%. So that is also met. Okay, so these are our new requirements. Now let's go ahead and find our critical value and our test statistics. So I'm going to go ahead and sketch this. So let's go ahead and sketch. And remember that this is a chi-squared distribution with the degrees of freedom equal to k minus 1. K is the number of categories. In this case, it's 4. So degrees of freedom is 3. I wasn't given a significance level, so I'm going to go ahead and say alpha is 0.05. So I can go ahead and find the critical value. So remember that we find that in StatCrunch. So we go to stats, calc, chi-squared. We type in our degrees of freedom, as well as indicate that we're doing a right tail where the area in the right tail is 0.05. So we observe our critical value. All right, so that should have been familiar. Now let's go ahead and emphasize the test statistic. So the test statistic is going to be quantifying the level of disagreement in category I. And so let's just look at each category. Let's see, what is O1 minus E1 squared divided by E1? So that's going to be 100 minus 80 squared divided by 100. So you could throw this into a calculator, or you could do it by hand if you want. Here on top, you'll get 20. So that'll be 20 squared divided by 100. 20 squared is 400. Oh, it's E1 over E1. So if E1 is 80, the bottom should be 80. So those should always match. Okay, so that'll be 400 over 80. So that gives me 5. So the level of disagreement in category 1 between the observed and expected gives me a value of 5. Do this for each category. Again, there's a level of disagreement. And just substitute your values. So 50 minus 40 squared divided by 40. Remember, these always need to match. And then here we get 150 minus 180 divided by 180 squared on top. And here we end up with 100 minus 100 squared divided by 100. So the only other point that I want to point out is this category 4. 100 minus 100 is 0. So that'll be 0 squared divided by 100. So that'll be 0. So notice that this makes sense. The level of disagreement in category 4, there is no disagreement. So that contributes 0. But the level of disagreement in category 1, that's a 5. Do this for all the other ones, and you get the level of disagreement as 2.5 and 5. So if you add all of these up, you get the chi-square statistic. So this gives you the chi-squared stat, which is going to be the sum of all of these. So that's 5 and 5 is 10, 12. So that's 12.5. So this is our test statistic, 12.5. So a total level of disagreement in the entire data set compared to the claim distribution is 12.5. Notice that 12.5 is in the critical region. And so therefore, we've shown that this level of disagreement is too extreme under the null hypothesis. So therefore, we're going to go ahead and reject the null hypothesis that we follow, right? That our data is going to follow the claim distribution. And that is more or less how we will compute this. Notice that at its core, it is very simple, because all we're doing is we're saying compute the expected counts, and then compare to the actual data. Find the level of disagreement and determine whether that's too much disagreement. And that is it. Let's go ahead and see how to do this in StatCrunch. So in StatCrunch, here's the command. Let me actually write it here. You're going to go to stats, goodness of fit, and then select chi-squared. So I already have my data in there. Notice that in StatCrunch, you have to essentially give it the data. So here's the expected. I computed that myself. Here's the observed. And then we're just going to go to stats, goodness of fit, and select chi-squared test. Notice they're saying, where are your observed? So this is your sample information. And then where is the expected? That is all you need to do. You press compute. And StatCrunch has gone through the work of determining the chi-squared test statistic. Notice it's 12.5. That is what we got. And they also find the p-value, 0.0059. So just like that, this is our goodness of fit test. So in the next video, we will do another example, more carefully developed. And that is the video that you want to make sure that you pay attention on how to set everything up. All right, thank you for joining me. I'll see you in the next one.